Okay, so I'll show you some. This is what the theorems actually look like. I sometimes ask you to write in mathematical notation. We had to write the whole thing out, seize the order, blah, blah, blah. The maximum cycle length equals the order of the minimal polynomial. Sub-maximal cycle length equal the orders of factors of the minimal polynomial and the minimal polynomials. Thus, I can actually crank it out. Not hard to do. Just subtract lambdas down the diagonal and take the determinant of that, what's left. You can do it. It's actually not that hard. So how does this work? For n equals 17. This is what, if I multiply these two things up, I get this guy. I have one factor of lambda that I can take out. So on Mathematica, you can tell it to actually, the command is expand. You don't learn all the cool commands actually in 103, or even JEDI. I think JEDI, you're just going through and trying to get your tech labs done. But really the cool commands are that you can expand any polynomial, you can factor anything, you can simplify anything. Those are like the tools of Mathematica. And if you take that and expand it, you'll get these two polynomials. The order of this one is 85, and the order of this one is 255. What does that mean? For n equals 17, I have two different period lengths. One is 255, which Dennis found by hand, by just looking. We already knew them because he could see them. And the other one's 85, which he missed. He missed the submaximal ones. I don't know what happened to him. I don't even think he finished his degree, actually. I don't remember him finishing his degree. So n equals 2 to the m times r. You were talking about the cycle lengths where you have 2 to the m. You can just pull it from the minimal polynomial immediately. So there's nothing there. You can actually get everything quickly. And you can get the submaximal cycle lengths. This might be too hard to understand right now. Proofs. These are how the proofs work. Just plug in the piece that you have. You can even plug in 2 to the m here. If you have 2 to the m, all the coefficients inside are 0 because they all have even coefficients. And in Z2, even coefficients disappear. And you're just left with 1 plus lambda to the n. And then 1 plus 1 is 0, so you just have lambda to the n. So that means that the order is going to be whatever n is. Was going to be, it's lambda to the n, the order of that is 1. Okay, so one last thing. I'll give you some open problems here. So what was the connection to Wolfram? Stephen Wolfram is a brilliant, brilliant person. He is known for developing Mathematica. I remember when Mathematica was first developed. It was in the 1990s. I think he started out with something called Derive. And he's a physicist, and he wanted to find a way to write code so that you don't have to do algebra anymore. And so this first shop of code came out in the 1990s, and I thought, I can get my PhD, because I don't have to do algebra anymore. And so I know my algebra teacher was like, so you went and got your PhD? Yes. Wolfram's Mathematica just came out, so it was a life-saving device. But another thing that Wolfram was really big on was cellular automata. And cellular automata are just rules. This is a rule, actually. You take the thing and do this. That's what we call a rule. You take that initial condition and you apply these rules. You can program it in Excel. And so his rules were all on zeros and ones. And he colors the ones by black and colors the zeros by white. And you see these beautiful patterns start to show up. So you can create Sierpinski gaskets with this really complicated designs from just very simple rules. And so there's a whole bunch of his rules that are online. He wrote a book called A New Kind of Science. I think around the time I was in graduate school, he wrote that book. And these books, the things he writes, people get really up in arms about it because he's kind of his own person. He just does his own thing. He has his own company now. And you know, he doesn't follow the way we do academics. He's a very, very cool person. But you know, he decided that he's just going to make Mathematica and do his own thing and have Wolfram Math Pages and Wolfram Alpha. And he hires a lot of math students to work for him. Yeah, he's a really amazing person. But you can check out these rules. The one rule that got a lot of mathematical attention is this one. He wrote it with Martin Nodlisco. And really what it is, this is the rule up here. It's written in a different way, but it's almost like Ducci. Ducci says take one and then add to the right. Take one and add to the right. Take one and add to the right. This one says add to the left and right. To get the next center point, add to the left and right. Add to the left and right. And so this is very similar. And so they had done some work on this, I think back in the 80s. And I don't know how, but we just noticed that the patterns almost look the same. So because we could spit out all those orders, and we could spit it out for wolframs also, we found the connection that the order of Ducci is equal to the least common multiple of n in the order of wolframs. So there you have it, all the cycle lengths of both of them. Just imagine, I think Dennis finished up at 19, around 19 he was toast. He found, I think, the 19, this one, by Excel. By looking at it and counting. Yep. And then you see, like, if you really look at we look at this and go, what's the relationship between this side and that side? How do we look at that and find that? So we had to really think about what was the relationship between the two sides. And then combinatorics. We were counting how many vectors are there that lead to a periodic cycle. So all of these three results are on combinatorics. And you can actually look at the cellular automata as graphs. So it's graph theory and combinatorics. That's why I love this problem. It has so much mathematics in it, but you can just start with Excel. Anyone can start with Excel. Another thing mathematicians do is we generalize. So we look at what we have and ask ourselves, does this work for what we're doing, or does it work for some general thing? So in one of the papers that we published, it turned out that there was more a general example. And so we wrote that one, and you see the embeddings. So topology is in here, embedding. So the big problem, can you write down what the function is going to be for the period as a function of the string length? That's still open. No one has a formula for that yet. There's all kinds of cellular automata, and I haven't looked at any other ones than Wolfram's model that he talked about in that one paper. I'll show you a couple of them on the board, but there's all kinds of cellular automata that actually work this way, and I don't think anyone's looked at it this way, as far as I know. We have like a list of open problems, but you can sit down and think of your own just like that, looking at this.